All right, welcome back to Kitchen Research Group. I'm going to talk today about the scimax channel, and this is a continuation of a video I started a few days ago on using scimax, org mode, Emacs as an electronic laboratory notebook. And we're trying to explore principles of fair data, findable, accessible, interoperable, reusable, and how we can or can't do that with org mode. And org mode is, if you're not familiar with it, it's kind of very roughly like a Jupyter notebook. We have narrative text, and we'll have code interoperable, and a lot of the issues that I'll talk about here are also present in Jupyter notebooks, but I prefer org mode and have used it for a long time. So last time we looked at just a simple example, Python computation, science, and engineering. And that simple example was just solving this particular problem of a plug flow reactor. I work in chemical engineering. You can substitute your own problem for this, and you'll run into the same issues, where we wanted to find the exit concentration of this reactor for different values of this rate constant. And it's just a simple initial value differential equation. You integrate it, you get the exit concentration, do it for 3 different Ks, you get 3 different answers. And what I showed you was that, and we'll look at the notebook that I made last time, a lot of the data is gone. It was in memory at the time, and I closed that notebook, and now the data is gone. So for example, here is one of the things we worked out. You can read the code, you can see the output. But the solution variable, everything about the message, everything that we had at the time in memory is now gone. And the only way to retrieve it is to rerun this. And it is okay to rerun it. In this case, it's super cheap. It doesn't cost me anything. But if this was something that was running in a cloud lab, or if it was expensive and took a couple of days to run, then you would not want to rerun this just to get back to some of these intermediate states. And this data is not really addressable, so there's not an easy way for me in another notebook to extract this particular number. There's no name or address or URL associated with it. This block doesn't have a name associated with it. And this is the solution data. I printed it here, but this is not actually reusable in a reasonable way. And then I solved this 3 other times, and we didn't save this anywhere but this plain text. We did run it in a loop, and then down here I showed you an idea. We could take the data and dump it into a JSON file or CSV file, any kind of file that is your favorite format. You can persist it to disk by writing it to disk. I didn't talk about it so much, but we had to pick a name, and picking names is hard, especially when you have to pick a lot of names. So it's not really ideal for a large data project. Let's say we're running 1,000 calculations. You have to come up with 1,000 names, and then you have to know how to find and use them. So that's not ideal. But this data file is interoperable, so I could use JQ down here, for example, and extract data from it. And you could use any other package that has a JSON parsing library. So today we're going to look at a more automated way of solving this problem. I'm going to go ahead and copy this code because I'm going to reuse parts of it. And we're going to look at a package called joblib. So let me show you what joblib is. And make it a little bit bigger. So joblib is a Python package that claims to be for running Python functions as a pipeline job. And here's what I want to get to down at the bottom is that we can use it to avoid computing the same thing twice. So it's going to store the results in what's called a cache, and it's going to store that on disk. And so that means that later we can look it up. The way this works is that you have to create a function, and then you have to decorate the function with this mem.cache decorator. So we're going to import joblib, define a directory, create a memory, and tell it where to store the results, and then we'll decorate an existing function And then every time we run that function, it's going to store something in the cache. And then if we try to run it again, it's going to look it up from the cache. So that's the main task that we want to look at today. So I'm going to make a new page here, and I like to use like a journal. Among the things that are hard to name are pages in your notebook. So I use a Scimax journal, and it creates a page here with the date. So this is going to go in a folder called journal, year, month, day, and then you see the file name down here. That happened automatically. I don't have to do that. If I make a new file tomorrow, then it will make a 0616.org file. All right, so I'll add a headline here. And let me paste that code that I put in here and tell you what we need to do. So the strategy here is we're going to make a function that solves our problem, and the function will have an input. Let's say it's the k value, and it will output the solution. And then we're going to decorate it with the cache decorator from joblib. And so let's go ahead and get some of these imports going. So we have to import memory from joblib. And then make our function. So from joblib import memory, and go back and just refresh my memory here. So we need to make this line here. And I'm going to just use the current working directory. This is already a little bit tricky. You have to know how the notebook interacts with Jupyter Python. And so the current working directory dot is actually going to be the directory this file is in. So it's going to store everything in the local directory. And now I need to make a function. So let's do def. I'm just going to call my function solution. And let's take one argument for k. We'll keep these things all the same. We can define our ODE inside of it, and then we'll return the solution. All right, so now I should be able to run this. Let's check it before we do anything. And this should run, and it has given me the solution that I want. It's not currently cached anywhere. And to do that, I have to add this mem.cache solution here. But I'm not gonna do that quite yet. I want to add one more piece so that it's obvious when this runs and obvious when it doesn't. And to do that, I'm going to make it play a sound. So there is a cool little Python library called Nava, and it will play a sound. And I found a sound before that sounds like a little cache register. There it is. And so I'm just going to insert that sound, and now when we run this, you can hear it make a little ka-ching sound, and that's an indication that it's costing me money to run this. And this is why I don't want to run it every single time I get 0.1, because it does cost us something. It costs us some time. If it's in a cloud lab, it's going to cost you money, and if it's expensive, it could cost you time and money. So that's why it's helpful to be able to save and store this. And so now let's go ahead and add this decorator. And I'm going to use a good habit here and just have this defined in one cell. And so now let's see what happens when I run this for 0.1. Now, the first time I run this with that decorator, you're going to hear the ka-ching. And you'll see the output here. It's going to have something new. It says memory, calling underscore main something something. And then we have a solution here. Now let's look at what happens when I call it a second time. So if I call this a second time, we don't hear any ka-ching. It's just looking up a result from the memory that it's written. And so we already have a benefit in using this decorator, that we don't have to run the equation, that function twice. The second and third and fourth time, it will simply load the previous results. Now, where do those results live? Those results live in the directory. Let's go back up to the top that we defined the memory in, and that's in dot. Dot means current working directory. And so let's look here at what we have. So this is the current directory that I work in, the full path. And this is the file that I'm working in, and that joblib is the directory that joblib creates. So if I go inside that, you can see here is that sort of strange looking path, /var/folders something. This looks like a temp directory that is created probably by the Jupyter kernel. This is where the Jupyter kernel thinks its path is. And then inside here is a another directory called solution. That's the name of the function that I ran. And inside here is another directory that looks like a get hash. It is actually a hash of the arguments, I think, and maybe some other things. This is the function code that we actually ran. And so that's kind of cool. It stores the code that ran it. That might be useful later. And then inside of here is a metadata.json object that gives you the time it took to solve it and the input arguments that were used. We'll come back to this idea a little bit later when we talk about findability. And then there's this output.pickle, and this is a pickle file that is a format that Python uses to serialize results. So here it has taken that ODE result. You can see a couple of plain text things, and it has serialized it to a byte string. You see all these backslash characters. These are bytes that Python knows how to unpack into the original solution object. Now, this is going to cause a problem with interoperability because I don't know of any other packages or languages that can read a pickle file besides Python. And even between different versions of Python, you might have trouble reading this pickle file. So pickle is super convenient because Python can take the byte string representation of your objects, anything you have in memory practically, and represent it in this form so you can use it later. But it's not convenient if you are using other languages and you want interoperability. So we have moved a step forward in being able to automatically save these results for future use. And but it's come at a little bit of a trade-off in interoperability. Okay, let me show you a couple of other potential concerns here on whether this is actually a good solution or not. So I'm using Jupyter Notebook here, and there's nothing wrong with Jupyter Notebook. It's very convenient. You get all of these cells. But let's take just a quick moment and see if we run this in Python. So this is going to run in a slightly different way, where the Jupyter Python creates a Jupyter kernel, communicates with it, the kernel's still alive. This green block here is ordinary Python. It's going to get written as a script, and then it's going to evaluate the script. And here is one of the first places where I think we might find a surprise. Since I have already run this a very exact function, you might expect that it should be able to look it up and get the result without hearing a ka-ching. And let's see if I run this, what happens. I heard a ka-ching. That means that this function actually got run. And oh, this is interesting. So this doesn't show the last line. I have to, let me just add return here. I think when I run it this time, we will not hear a ka-ching. No, nope, we do. That happened because it cannot detect name collisions for function solution. It has a different cache now. Let's look at what happened in here. So now you see we have two different paths. So as far as Python is concerned, the path to this script is different than the path to Jupyter Notebook, and so we're not able to avoid running things more than once. And I find that to be a surprise, but that's because joblib is including path information inside the way it stores the results. And if you run it by Python or run it through Jupyter Python, we get different paths, so we get different results. I think that is like not all that desirable, but I'd say that's a feature of this particular implementation of a hash. So let me just write some of these notes down. So what that's going to result in eventually is that the hash idea is a great idea. It provides automatic naming, so you don't have to come up with a name, and it's deterministic. So you know if you do things the same way each time, you're going to get the same hash. That way you can look it up. But it's also fragile, and it's fragile in the sense that if you change anything, that even like moving this script to another directory, then odds are very high that you will not be able to reliably use the hash. Let me do one more version of this just to maybe drive that point home. Here, if you understand how org mode works, you know this is a script that's only in org mode, and when you run it, it gets written to a temporary file or it gets piped into standard in. Let's do a version like this. And here I'm going to tangle this. This is org mode literate programming text for write this out to a file. And so let's do that. So now there should be a file called solution.py. It has those contents in it. And let's go back up here, and I'm going to run this one as a shell command. So let's do python solution.py. Oh, I have to get rid of this. Let's turn this into print. All right, now when I run this, we heard a ka-ching. That means we ran our function. And if I run this again, let's see what the output is. The output shows what we got. That's not a surprise. Now if I run this again, it should not make a ka-ching. It doesn't, and it just outputs the results. Okay, but again, now let's look in our joblib. Now we have three different things, and that's because of this path. So this bottom one with the temp folder, that was from the Jupyter kernel. When I ran it from Python in org mode, I assume something like this would happen in a notebook if you used a Python magic. And then down in this middle one is when I ran it from the Python script. So three different paths, three different runs. That's obviously not good. And you can now anticipate if I ran this from another machine, the same thing would happen. We would get a fourth folder, and now we have inside of here all these different runs for the different ways that I ran it. Okay, so that's one kind of limitation or feature, I'd say, of doing this. But it's fine. You know, I won't say nobody's going to do this. Lots of people will try different things for different reasons, and there's just no telling how you might integrate running a shell script with running a Python script with something in a Jupyter notebook. When you're trying to get things to work, you're trying to get things to work, and this is how I discovered this particular kind of limitation. Okay, let's go back here and let me run my. Let's do what we did before with the loop. K. Let's do K is 0.1, 0.2, and 0.4. And then let's do f is solution of k for k and big K. This is what I did before. Now when I run this, it should retrieve the results for point 1. Maybe we should make this be the solutions, because each of this is returning the solution, and then it should run for point 2 and point 4. So we should hear 2 ka-chings when I run this. In fact, that's what we see. And you can see here it tells us that it was writing the 2 results for point 2 and point 4. And then if I want to get the actual f's in here, now I have to do another list comprehension. And so it's going to be sol.y bracket 0 minus 1 for sol in that list. And now this is retrieving those results that we got before, and we could do something with them. Make a graph, a bar chart, something like that. So we've made a step forward, and the critical ideas on this are that when we run this, that decorator is computing a hash of some properties of the source code and the arguments. You'll have to read through the, let's see if we can look at it here. Here's the cache code that takes a function. It doesn't really help to read this code. You have to go back into this memorized func and see what kind of stuff happens. But there's a bunch of options here I didn't really talk about. You can choose different backends, different ways that it is stored. Maybe I can look at this one. So there's a hashing function in here that you can get argument hashes. A function hash, so it's using something with online code, etc. All right, but I want to talk about some other issues that I have run across. The hash is, as I said, it's brittle and fragile. And so if you make any changes to this this function at all, even changes that don't matter, like adding comments or adding doc strings, then it changes the function and you'll have to run it again. So to see what I mean, let's add just another line and a comment here. And this doesn't change anything as far as the output is concerned, and the comment will be ignored by the compiler. But look what happens when I run this again. We get a ka-ching. That means that it executed that solution again, and if you were running an experiment, you would be, you'd get a bill. So that's a feature of using the source code in the hash, is that any change at all, the change in the spacing, change in a comment, if I add a doc string, like this, and we redefine this, then when I run this, we get a ka-ching. So you have to be really careful that you don't change these kinds of functions. And for things like solve-IVP, that's probably okay. Although if you update SciPy, you may find, depending on what you've done, that might happen. Actually, let me be careful about that. If you are decorating a third-party package to make sure it gets cached, then that could happen. If solve-IVP changes, then this function won't change. So let's have a look. Let's see what I mean by that. All right, so let's do Let's say I have a function, let's just call it def f of x, and this is just going to return, 2 times x. And then let's do mem.cache. Let's cache a function g of x. And return x f of x squared. And let me add that sound in here so that we can easily hear when that function is run. All right, and now if I say, let's define this, and now let's do g of 1. Sounds good. And if I, that has an answer of 4. Does that make sense? F of x squared, that's 2 of x. Let's change this to 4 now. And I probably should have defined these in separate cells. Let me define them in separate cells so that we can define this one separately from this one. Now, if I run this, it's just going to retrieve 4, and that's obviously wrong, right? This is changed, but the signature and the hash for this have not, and so this internal state here doesn't get captured. Now, if I define this again, then this will work, and it will run. But if I keep changing, this outside function, then nothing else is going to change, and this is still, this will end up being incorrect. Now, this is not a totally contrived example. This can happen with global variables. So if you have a variable that is set outside your function, then it doesn't change the hash. So joblib doesn't track global state, and it doesn't track dependencies. Right, so here the idea is g of x depends on f, and so if it doesn't track that dependency for you. It can also happen if you read data from a file. So if you have any function that reads a file, a configuration file, an input file, some other file, and you change that file outside the function, it doesn't change the function hash. And so that's going to lead to potential for a surprise. And there's lots of packages that use an initialization configuration file or external global variables for it. So you have to know that this cache is really for quite pure functional kind of function where the inputs fully determine the outputs. And that's not the case here because of this dependency. All right, so I would call that a limitation if you're not really like in the weeds of functional programming, and you really and your functions are very pure so that the output only depends on the arguments. You're going to find potential for things that can surprise you. Okay, so let's get back to our questions and talk about what does findable mean here. So findable means, it really means you can find a result, and but that's not a really well posed statement. You have to know where to look to find something, and you have to know how to ask for it. So, for example, if I know I've run these results, the way you find, air quote, find this is you simply rerun your function again with the same arguments. And then you'll get the results. But that's also like a needle in a haystack. If I ask for another result that hasn't been run before, then it will trigger a function evaluation. That may or may not be a desirable idea for you. So let's just explore what's happening in here. So I know all of the results will be in joblib. You might not know that, but I know that. And if you read through the documentation of joblib, that's where you'll find it. And then inside of here, this is interesting. We have, I think joblib's not really meant for running in a notebook because we get all these like kind of weird kernel directories that show up. But let's just pick one. And inside here is a directory called solution. And inside of those are the directories called hashes. And inside those are directories called metadata.json. And then we have the output.pickle. All right, so, and then inside metadata.json, we have this. So let me go back to here, and let's talk about finding what we've done. So in a way, we can just say like, well, what is inside all of our metadata.json files? And so there are lots of tools for finding those. Let's do find joblib -name metadata.json. I think this is the shell command that would do that. I should not have hit shift enter. So we get a list of these, and then we could use these and search each metadata.json for input args. This is I've only had the one function solution in here, so you might want to filter these by solution as well, but I'm going to skip that particular step. I can do this in Python too, I think. So let's import glob, and let me import JSON, and let's look at glob.glob of joblib. Let's try this, metadata.json. Maybe it's this. Oh, I have to make recursive be true. Okay, so this gives me a list of all those files, and then we could iterate through them for f in glob.glob with open f as f json dot load s maybe. Let's see if we can get the input args. All right, so we can go through and find anything. Oh, it's actually I did have some extra functions in here, so it might actually make a lot of sense to filter this because we have the g of x that I had in here. Anyway, this is sort of an indication that it is possible by brute force search to find what you want in here, and that's just by traversing that file system and looking for what you want. It's not ideal, but if you have to use a database, then we are going to find ourselves in the position of having to learn how to use a database, and we're not there yet. So here at least you can glob through here, and you'll get an F, a file from one of those. That file will have a path, and you could even do something where you strip off the last bit of F and then use pickle to load that result for doing it. So I don't think I'm going to get into that today. Other than to say it's probably possible. That certainly is possible. So you might look through here, and maybe we could do one more step. Let's say we want to find out if it's 0.4. It is worth noting this is a string. That's kind of a curious that it's not stored as a float. So that you'd have to know what you were looking for here. But I could say if this input data equals, say, this dictionary, then we could print F. That would be the path that it's equal to. I should probably make this an underscore, so I'm not redefining it. So this is where that particular file is. We could do some pathlib work, so we could strip off the metadata.json. I guess I will get into it. Let's import pickle and import pathlib. And so we'll say from pathlib import path. Let's do that instead. And then I want to, we could have globbed directly from path. That would have been a good idea. Let's try path. Let's see what that .name is. That's the name of the file, and I probably want parent. That's the path to there. So let's say pickle. I never remember how to use pickle. Pickle is about object serialization. Also note here, pickle is not secure. You want to really make sure you trust data, and like I said, it may not work across Python versions. It's Python specific. And I'm looking for pickle.load, so that's what I want. And so if I print this, I guess we just need one slash. No. File must have read and readline attributes. Well, pickle.load. All right. right, we'll just do it this way. Invalid load key. Let's see what else is here. Maybe we just use joblib.load then. Okay, so joblib.load must be doing some special magic that isn't simply pickle.load. But we can get this result back and use it for something later. Let's see what joblib.load does. So it is doing an unpickle. But it has obviously defined its own version of unpickle, and it's not just unloading it in some way. Okay. Either way, the point here is that we have, by using joblib, achieved some of our goals. We can find things. It's a little bit tedious to find. It's not a database. It's not a proper search in lots of ways. And if you have lots of different cached functions, you'll have to be way more clever than I was here. And so let's say with joblib, somewhat findable, definitely reusable, not interoperable, and accessibility is a tricky one because it has lots of different meanings. This will eventually, there will be things that are accessible. It's certainly locally accessible. And I probably will not commit the joblib directory to GitHub. Not sure it makes sense to, since it doesn't work across different machines and other kinds of ways. But we also found that there are some limitations. Joblib is not a total solution in the sense that even just running it, here we have like all these different directories related to paths and kernels. It's obviously not meant to be run in Jupyter notebooks, and depending on how you run it in org mode or is a Python script, you get different paths. And if I was to run the same exact Python script on another machine, it would put it in another directory. And so I don't think that makes it a great solution for a Jupyter notebook or an electronic lab notebook that will work across machines and potentially across users. So it's not going to be our long-term solution. But it does have a lot of very good ideas, and among those is this idea of a hash. So this hash is what makes it possible to look it up. And in another video, we'll look at a different hash solution that I've been working on. It does store the code, so you can see what version of the code you use, but I find it too fragile. If you make changes to the code that don't matter, it makes a new hash, and I think that's overly conservative. We do have the metadata.json, so that's a big plus. but we have the output stored in pickle, which makes it not interoperable. So that's the features of joblib. It's worthwhile kind of learning it. If you have a problem where none of those other issues I said are limitations, then it's a perfectly reasonable way to start. And but if you need any of these other features, then I think it's not the right solution in the grand scheme of things. Okay, so that's sort of it for this one. I think there are paths forward to use the hash, use JSON for storing it, potentially link it to a database. Probably it's going to be SQLite. We might look at something like that in a future video, and that would give you something that is much closer to a hash that allows you to almost automatically save data, and who knows what new surprises we'll find based on that in a future video. All right, that brings me to the end of using joblib in an electronic lab notebook, and with that I will sign off and see you next time.